Hi everybody, this is the lecture on section 6.2, two types of what are known as line integrals. So the first type is the scalar line integral. So I like to say, maybe let's call it the density mass line integral, because that gives you one good interpretation for what this line integral means. So consider a curve r of t equal to, x, t, y, t in 2D or in 3D. Okay, I'm going to really explain it in 2D, and then just at the end we'll just say what all that means in 3D. So you've got a curve. Now, so let me say that. We'll explain for 2 dimensions. Oh no, let's do 3 for now. So, the r of t, it traces out a path in 3-dimensional space where t is time. So you've got some small particle moving along this path. Let f, x, y, z be some 3-variable function measuring the density, in units mass per unit length along this curve C. Units mass per unit length. What we want to do is we want to define an integral that calculates the entire mass of the curve. So we will define an integral which calculates the mass of the curve. By the way, if f, x, y, z equals 1, then the total mass is just equal to the length of the curve. The total mass of C is equal to the length of C. So this curve, this integral, this density mass line integral, this scalar line integral, is going to measure the total density of this curve or this wire or something like that in units mass per unit, in units of mass, where you've got a density function in units mass per unit length. But if that density function is 1, then the mass is just equal to the length. It's a constant 1 units mass per unit length. So if we figure out what the length is, then we'll have that total mass. So this integral is a generalization of the arc length integral. So the integral we are about to define generalizes the integral a to b r prime of t dt, which is equal to the length of C. So we covered this all the way back in section, what was it, 3.4. Is it 3.2 or 3.4? All the way back in chapter 3. So we're going to get something that generalizes this. Okay? All right. So given that R of t is for a less than or equal to t less than or equal to b, split the interval from a to b into subintervals of length delta t equal to b minus a over n, and let t0 equals a, well, ti equals a plus I delta t. So we're splitting up the interval from a to b into these familiar subintervals. Same kind of trick we've been doing. Right, T1, T2, T3, and then B is T4 in this case. All right. So now take these points and plot them along the curve. So now I'll switch to a two-dimensional explanation. Right, so you've got your curve C given by your function r of t. And we're in 2 dimensions now. And it doesn't matter which direction we're going along the curve, so I'll leave these arrows out. The direction of travel isn't going to be important. So you've got these points, r of t1, and they're not necessarily evenly spaced, but, you know, just for effect, we'll put them at fairly regular intervals along the curve. T2, T3, R of T4, we'll say is here, T5, T6, T7. Now, what you do is you connect these points by straight lines. Not that one. Bing, 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 bing. And we'll call these straight line segments, so the one that ends at S1, we'll call, or at T1, we'll call it S1. S2, S3, S4, so on and so forth. Okay, so S3 goes from R of T2 to R of T3, S4, T3 to T4, this is S5, S6, S7. All right. Thinking of that density function as relatively constant on small intervals, so along small intervals. So when the SI's, well, when the delta t is really small, the density function, you know, which is continuous, won't vary much, is relatively constant density f of r of t I. So this is the xyz corresponding to this point, right, ti being here, of constant density f of r of ti on the segment si. That segment si goes from r of ti minus 1 to r of ti. Right, so the density, you take the density at this point, and if this is really tiny, then the continuous density function doesn't vary much. So you think of it as a constant. Therefore, the total mass of this little segment of Si is approximately, well, it's f of r of ti times the length of Si. Right? This is in units mass per units length times this, which is in units length. Right? And those labels cancel, and that gives you units mass. Right? Things become a lot easier when densities are constant. I mean, so it's sort of constant on each one of those little intervals. So the total mass of the curve C, right, given by r of t, is approximately the sum of the masses of the segments. The sum I equals 1 to n, f r t I, length s I. Right, where the approximation gets better as n goes to infinity. Gets better as n approaches infinity. Therefore, the mass is exactly equal to total mass is equal to the limit as n goes to infinity. Sum I equals 1 to n f r of ti length si. So starting to look a lot more like an integral. Except there's no delta t there. No delta t. We'll get it there. Okay? What is the length of si? Right, well, si, length of si, so this is f of r of ti. So what is that? That's, we'll just call it xi, yi. And this is r of ti minus 1. Right, and we'll just call that xi minus 1, yi minus 1. So the length, and this is si, the length of si is just given by the distance formula. And let's make a shorthand for the distance formula. It's the difference in the x-coordinates squared plus the difference in the y-coordinates squared. right? Change in y squared plus change in y and y squared, change in x squared plus change in y squared, square root, right? Just the distance formula. Difference in the x's plus difference in the y's, those things squared, square root. Okay, so going back to here, this is the limit as n goes to infinity. Sum I equals 1 to n f of r of t I, right, square root delta x squared plus delta t, or y squared. So now I'm going to put in that delta t there. So this is the limit as n goes to infinity. The sum I equals 1 to n f r t I delta x squared plus delta y squared, and now I'm just going to write delta t over delta t, right? Because that's just equal to 1. I was multiplying that whole thing by 1, right? So it doesn't change anything. So limit as n goes to infinity, sum I equals 1 to n f of r ti times. Bring the 1 over delta t inside here, you get delta x over delta t squared plus delta y over delta t squared delta t. Now I got that delta t. Right? That's what we wanted for an integral. What are these things? Change in x over change in t squared. Limit as n goes to infinity. In other words, as delta t goes to 0. What is the limit as delta t goes to 0 of change in x over change in t? It's just dx dt. And this one just dy dt. So this is equal to the integral, single integral, from a to b of f of r of ti, or just t, sorry, dx dt squared plus dy dt squared, come on, dt. So there's the total mass integral for that curve C. Now, what is this? Let's clean it up a little bit more even. Let's clean it up a little bit more even. Remember, right, what was the meaning of x and y? R of t, right, it was equal to, it's a function for the x coordinate called x of t, and the function for the y coordinate, y of t. So r prime of t is just equal to, just the ordinary derivative, right? That's dx dt, or x prime, and that's dy of t, or just y prime. So the length of r prime of t is equal to, right, this component of the vector squared plus that component of the vector squared, add it up, and then take the square root. So that total mass of C is equal to the integral from a to b f of r of t length r prime of t dt. So there it is. Now, when f is equal to 1, when f was equal to 1, that's just the length of C. Right? That integral is the length of C. We covered that back in section 3.2 or 3.4. I forget which one. 3.4, I believe. So now when you have this variable density, right, the total mass is that. Right? you just have that extra function f there, and that's the density function. All right, notice that, okay, we never really took into account what the structure of R was. There's always different ways of representing C, okay? We never mentioned what R of t is explicitly, right? So if R1 of t and R2 of t represent the same curve, if R1 and R2 represent the same curve C, then, I guess we got to give an interval, A1 less than or equal to T less than or equal to B1, and A2 less than or equal to T less than or equal to B2 represent the same curve C, then those integrals are going to be the same, exactly, right? Not the same expression, but the answer will be the same, no matter how you represent that curve. Oops. Come on. Try again. So if this is A1, B1, R1, R1 prime, A2, B2, R2, R2 prime, they're going to be equal. So it's sometimes nice to refer to the line integral, this line integral, without referencing R at all. To mention this line integral without making reference to R of t at all. Right? In this case, we write just the line integral over C f x y ds for the two variable thing, or the line integral over C f x y z ds for the three-dimensional situation. All right, so just the single integral over C, fxy ds or fxyz ds, right? And right, in each case, the integral over C of f ds, I won't even write that. You know, whether it's fxy or xyz is equal to the integral from a to b f of r of t length r prime of t dt, where c is r of t for a less than or equal to t less than or equal to b. And that can be useful because sometimes you can represent curves in lots of different ways, right? I mean, like with circles, right? We know how to represent circles in different ways. So why don't we do that as a first example? So for example, so let's calculate the integral over C of y ds, where C is the top half of the circle of radius 1 centered at the origin. Origin. Right, so this is C. So minus 1, 1, and 1. That's just a terrible drawing. This is not much better. The screen is, pen and screen is just so slippery, it's hard to sort of control where you're going. There it is. Okay. So that's the curve C. And again, the direction doesn't matter in this case. All right, and let's make the calculation in two different ways. Okay, so first, well, how do we do this top half of the circle? Well, sort of the usual standard way of doing it would be x is cosine t and y is sine t, right? And 0 is less than or equal to t is less than or equal to pi, right? So, well, we need to know what r prime of t is. Sorry. So method 1. So let's let me see. So method 1. So parameterize is a fancy word. C as r of t equal to cosine t sine t for 0 less than or equal to t less than or equal to pi. Right, and we need to know the derivative r prime and the length of r prime. So r prime of t, right, is equal to minus sine t cosine t, and the length of r prime of t is equal to square root of sine squared plus cosine squared t, which is just 1. Nicely enough. Right? So, the line integral over c of y ds is equal to, alright, let's write it out. It's the integral from a to b f of r of t r prime of t dt. Right, that's this is the integral, like, not mentioning r. Here's the integral mentioning r. So what is f of r of t? So r of t is x equals cosine t, y equals sine t. And then fxy, right, fxy is just y. Right, so f of r of t, x is cosine, y is sine, is just sine of t. And then the length, r prime of t, is just 1, right, and we're going from 0 to pi dt. Right, so it's just the antiderivative of sine, which is minus cosine, integral from 0 to 1, or pi. So this is 1 minus 1, right, so this is 2. So that line integral is 2. Let's parameterize in a different way. Parameterize c as r of t. And here's a trick you can always use. Right, the unit circle is x squared plus y unit circle. Circle of radius 1 is unit circle, x squared plus y squared equals 1. right? And we're just doing the top half, so it's y equal to 1 minus x squared. So there's a function y equals f of x that gives you that curve in 2 dimensions, y equals f of x. In 3 dimensions, no, this only works in 2 dimensions. Well, the trick I'm describing here. If you've got this y equals f of x, just let x equal t, and then y equal f of t. Right, so that's the circle. X squared is t squared, plus y squared, 1 minus t squared, equals 1. Right, that's just the circle. T, f of t. And what is the range for t that we're using here? From x going from -1 to 1. X going from -1 to 1, which is, t. So the x represents the t. So going from -1 to 1, and then the y goes from 0 to 1 down to 0 again. Right? Okay. So we need to know r prime of t. Well, r prime of t is equal to 1, and then this is equal to 1/2, 1 minus t squared to the -1/2 times minus 2t, like that. So that's equal to 1, and then the 2 and the 1/2 cancel, minus t over square root 1 minus t squared. So that's r prime. And we also need to know r prime is the length. Well, that's the square root of this squared plus that squared. 1 plus t squared over, so minus t over square root 1 minus t squared, that quantity squared. So this is 1 minus t squared over 1 minus t squared plus t squared over 1 minus t squared, which is 1 over the square root 1 minus t squared. Okay? So the line integral over c of y ds is equal to, again, let's just write it out, integral from a to b, f of r of t, length of r prime of t, dt. Right? Let's just write this out each time, just so we know where we're at. Alright, so a is -1, b is 1. What is f of r of t? Right, well, fxy is just equal to y. Right, and what's r of t? X is t, y is square root 1 minus t squared. So y, f of r of t is just 1 minus t squared. Right, that's just the y. So this is, you replace y with this, and if you had an x there, you'd put the x with it, but there's no x there. So it's just square root 1 minus t squared. That's the y. And then length of r prime of t is this, dt. Well, nicely enough, those cancel. Integral from -1 to 1 of just 1 dt, which is 2, because the length of that interval is 2. Same answer. Same answer each time. Okay, so we'll do a lot more examples during the Q&A period, but let's end this part of the lecture right here, and I will post a second part of the lecture on the next line integral so the video doesn't get too long.